Okay, so our next topic is eigenvalue and eigenvector. So first we'll learn eigenvalues and then we'll see how to find eigenvectors. But before understanding those topics, we have to learn about this characteristic equation. So the definition of characteristic equation is, let A be any square matrix. These quantities, eigenvalue, eigenvectors, are defined only for square matrices. So let A be any square matrix and I be identity matrix of same order. Then this equation, determinant of A minus lambda I equals to 0, this equation is called characteristic equation. See, from here you will get A is known matrix, A is given, I is identity matrix. So from here you will get some polynomial equation in lambda, and this polynomial equation in lambda equals to 0. This equation is called characteristic equation. Now the roots of this characteristic equation are nothing but the eigenvalues. So the roots of the characteristic equation are eigenvalues. Now with the help of one example, we will see how to calculate the eigenvalue of any given matrix. So suppose the matrix that we have is, we have a matrix A of order 2 into 2. The first row is 1, 2, the second row is 2, 1. And we are interested in finding the eigenvalue of this matrix. So first step is we have to find this characteristic equation, and then we can solve the characteristic equation to find eigenvalue. So the question is, find eigenvalue of this matrix A. So first step, you have to find the characteristic equation. So characteristic equation will be determinant of A minus lambda I equals to 0. So from here you can easily see that this A is a matrix, lambda is some scalar quantity. Maybe I should write these things. A is the matrix 1, 2, 2, 1 minus lambda I is the identity matrix. Now since A is a matrix of order 2 into 2, I will be a second order identity matrix. So 1, 0, 0, 1, and determinant of this matrix equals to 0. This is your characteristic equation. So now we can rewrite this equation as, this will be matrix 1, 2, 2, 1 minus, now if we multiply this identity matrix by lambda, I will get lambda here and lambda here. So this will be lambda 0, 0 lambda, and determinant of this matrix equals to 0. Now you can see that this will be, we have to subtract lambda from the diagonal element. So I will get 1 minus lambda, 2, then 2, 1 minus lambda, this equals to 0. So this is your characteristic equation. Only to explain the concept I have written all the steps, otherwise you can directly start from there. Determinant of A minus lambda equals to 0. After this, our next step will be subtract lambda from the diagonal elements. So our matrix was 1, 2, 2, 1. So we have simply subtracted lambda from the diagonal elements. So 1 minus lambda, 1 minus lambda. Now this equation is called characteristic equation, and we have to solve this equation to find eigenvalues. So if I expand this determinant, I will get 1 minus lambda square minus 4, this equals to 0. So this means lambda minus 1 square, this will be 2 square, which means lambda minus 1 will be plus minus 2. Now if you take positive sign, then lambda minus 1 is 2. This means the value of lambda is 3. So one of the eigenvalue is 3. And if I take negative sign, then lambda minus 1 is minus 2. So this means the value of lambda will be minus 1. So these are the two eigenvalues, minus 1 and plus 3. Our matrix A is 1, 2, 2, 1. So the eigenvalue of this matrix will be 3 and minus 1. So these are the eigenvalue of the given matrix. Now see, for any matrix it is very easy to calculate eigenvalue, especially if it is a 2 cross 2 matrix or maybe 3 cross 3 matrix. But in GATE exam, mostly the questions are asked based on the concept of properties of eigenvalue. So after this we are going to discuss 6 different properties of eigenvalue, and with the help of those properties we will see how to calculate the eigenvalue. So the first, because in exam the options will be given, and from the given options we have to identify which of the options are correct. So our next heading will be properties of eigenvalue. So the first property is, first let me write properties of eigenvalues here. So our next concept is properties of eigenvalue. Now total we will see 6 different properties, out of which the first 2 are very, very important. So the first property is the sum of eigenvalue in any matrix, the sum of eigenvalues in any matrix is always equal to, sum of all the eigenvalues in any matrix is always equal to the sum of diagonal elements. Sum of diagonal elements. So this is very, very important property. Now let me write the example that we have just discussed here. The matrix that we had was 1 2 2 1, and the eigenvalue of this matrix was -1 and +3. These are the two eigenvalue, -1 and +3. Now the first property says that the sum of all the eigenvalue is equal to sum of diagonal elements. We can write that in this manner: summation lambda I. This will mean sum of all eigenvalue, lambda 1 plus lambda 2 and so on, and this will be equal to sum of diagonal elements. So here you can see that we have two eigenvalue. One eigenvalue is -1, other eigenvalue is +3. Now if you add these two eigenvalue, you will get -1 plus 3 plus 2, and if you add the diagonal elements, these are the diagonal elements 1 and 1. So if you add that diagonal elements, then also you will get 2. So this is very, very important property. Sum of all the eigenvalues is always equal to sum of diagonal elements. Now see, sometimes this sum of diagonal element is also given a special name. This is called trace of the matrix. So we can write that summation lambda I is equal to trace of matrix A. Lambda I are the eigenvalues of matrix A. So sum of all the eigenvalue is always equal to the trace of the matrix. Trace is nothing but sum of diagonal elements. Sum of all the diagonal elements is called trace of the matrix. So this was first property. The second property is, these properties are very helpful in eliminating the options. In gate 4 options will be given, and from there you have to identify which of the given option is the possible eigenvalue of given matrix. So if you know these properties, then you can directly eliminate the options. So the first property is sum of all eigenvalue is equal to trace of the matrix. Then the second property is the product of eigenvalue. The product of all eigenvalue. The product of all eigenvalue is equal to the determinant of the matrix. So sum is equal to trace of the matrix and product is equal to determinant of the matrix. So if I have a number of eigenvalue, and if you multiply all those eigenvalue, lambda 1, lambda 2, lambda 3 up to lambda n, for nth order a square matrix you will have n eigenvalue, and if you multiply all those eigenvalue, then this value will be equal to the determinant of matrix. So again, this is a very, very important property, and this you can verify here also. If I multiply these two eigenvalues, then I will get -1 into 3. The product of eigenvalue lambda 1 into lambda 2, this will be -1 into 3 minus 3, and if you calculate the determinant of the matrix, then determinant will be 1 into 1 minus 2 into 2. So this will be -3. So sum is always equal to sum of eigenvalue is always equal to sum of diagonal elements. Sum of diagonal elements is also called trace of the matrix, and the product of eigenvalue is always equal to determinant of the matrix. So these are the two basic properties. Now the next property is related with eigenvalue of diagonal matrix, lower triangular matrix and upper triangular matrix. So now we are going to discuss the third property. So our third property is, in case of diagonal matrix, the definition of diagonal matrix was Aij is 0 for all I not equal to j, meaning that all the off diagonal elements are 0, then the matrix is called diagonal matrix. So in case of diagonal matrix, upper triangular matrix, in case of diagonal matrix, upper triangular matrix and lower triangular matrix, in these three matrices, lower triangular matrix, diagonal matrix, upper triangular matrix and lower triangular matrix. These upper and lower triangular matrix are simply those matrices in which the element either above the leading diagonal is 0 or below the leading diagonal is 0. So in case of diagonal matrix, upper triangular matrix and lower triangular matrix, the eigenvalues are diagonal elements. So this is again a very, very important property. In case of these matrices, you don't have to calculate the eigenvalue. The eigenvalue will be simply the diagonal elements. So let me give you an example. Suppose if I have a matrix, say 2 0 0 0 3 0 and 0 0 4. So if I ask you what are the eigenvalue of this matrix, so you can see that this matrix is a diagonal matrix. All the off diagonal elements are 0 and the diagonal elements are 2, 3 and 4. So here the eigenvalue of this matrix will be simply the diagonal elements 2, 3 and 4. These are the 3 eigenvalue of this matrix. And see, it is very easy to identify, very easy to verify this property. If this is the matrix that you have, then in order to find eigenvalue, you have to solve the characteristic equation. Now the characteristic equation is nothing but a determinant of a minus lambda equals to 0. So this means we have to subtract the lambda from diagonal elements. So I will get 2 minus lambda, 0, 0, 0, 3 minus lambda, 0, 0, 0, 4 minus lambda, this equals to 0. Now if you expand this determinant along first row or first column, then what you will get? You will get 2 minus lambda, and this multiplied by 3 minus lambda, 4 minus lambda equals to 0. So 2 minus lambda, 3 minus lambda, 4 minus lambda, this equals to 0, and this means the value of lambda that you will get is 2, 3 and 4. So these are the eigenvalues. So same thing will happen if the matrix was triangular matrix, either lower triangular matrix or upper triangular matrix. For example, suppose if I had any other matrix, say here if I had the numbers 1, 2, 3. So now this is an example of triangular matrix. This is upper triangular matrix because the element below this leading diagonal is 0. Now here again, if you have to find the eigenvalue, then what you have to do? You have to solve the characteristic equation. So I will get 1, 2, 3 here. But this characteristic equation will not change. You can see that if I expand along the first column C1, then I will get 2 minus lambda, 3 minus lambda, 4 minus lambda, minus 3 into 0. So this term will become 0. So you will get the same characteristic equation. So whether the matrix is diagonal matrix or upper triangular or lower triangular, the characteristic equation for all the three will be same if the diagonal elements are same. So in that case, these diagonal elements will be simply the eigenvalues. Now another important property that in case of these three matrices that you can think from here is, we have just discussed that in case of any square matrix, the product of eigenvalue is equal to determinant, right? We have seen this was our second property. Product of eigenvalue lambda 1, lambda 2, lambda 3 up to lambda n. This was nothing but determinant of matrix. And we have seen that in case of diagonal matrix, upper triangular or lower triangular matrix, eigenvalues are nothing but diagonal elements. So this means in case of these three matrices, we can say that determinant will be also the product of diagonal elements, because product of eigenvalue is the determinant of matrix and eigenvalues are nothing but the diagonal elements. So this means product of diagonal elements will be determinant of matrix. So for these type of matrices, you don't have to calculate the determinant. Suppose if I have a lower triangular matrix, say if I have a matrix like this, 2, 0, 0, 3, 1, 0, 4, 2, 6. Suppose this is the matrix that we have. This is an example of lower triangular matrix because element above this leading diagonal are 0. Now here if I ask you what will be the determinant of this matrix, so you don't have to calculate the determinant. You can simply multiply the diagonal elements to get the determinant of this matrix. 2 into 1 into 6, this will be the determinant of this matrix because these are the eigenvalue. 2, 1, 6 are the eigenvalue and the product of eigenvalue will give you the determinant. So again, this is a very important property. In case of lower triangular, upper triangular and diagonal matrix, eigenvalue are the diagonal elements and determinant is the product of diagonal elements. So this was our third property. Then fourth property is, if lambda 1, lambda 2 up to lambda n are eigenvalues of matrix A, if lambda 1, lambda 2 up to lambda n are the eigenvalue of matrix A, then eigenvalues of A to the power n are, maybe I should change the number, A to the power m are. So you know the eigenvalue of this matrix A, and now you are interested in finding the eigenvalue of A to the power m. So the eigenvalue of A to the power m, this will be nothing but mth power of all the eigenvalues, lambda 2 to the power m, lambda 3 to the power m, lambda n to the power m. So this is our fourth property. Now I will explain that property with the help of example. It is always better to understand with the help of examples. So our first problem was that we had a square matrix A and this was 1, 2, 2, 1, and the eigenvalue that we had seen was minus 1 and plus 3. Now these were the eigenvalue of matrix A. Now here if I ask you what are the eigenvalue of A to the power 10, A to the power 10 will be this matrix 1, 2, 2, 1, this raised to the power 10. We have to multiply this matrix 10 times to get A to the power 10. Now if I ask you what are the eigenvalue of this matrix, so you can, using this property, you can directly write the eigenvalue. Eigenvalue of A is minus 1 and 3. So eigenvalue of A to the power 10, this will be minus 1 to the power 10 and 3 to the power 10. So these are the eigenvalue of the matrix A to the power 10. So this is the first part of, this one is the first part of fourth property. The second one is if lambda is eigenvalue of, if lambda is eigenvalue of matrix A, then eigenvalue of some polynomial in A. So you have a matrix, matrix which is some polynomial in A. So this is P of lambda. Now again let me explain this thing. Suppose if I have a matrix A and its eigenvalue are say these numbers minus 1 and 3. And now we have now we want to find the eigenvalue of this matrix, say 2 into A square minus 3A plus 4 times identity. You are interested in finding the eigenvalue of this matrix. So in order to calculate the eigenvalue, if you know the eigenvalue of matrix A, then you can directly find the eigenvalue of this matrix. Simply substitute these numbers minus 1 and 3 in place of A. So corresponding to minus 1, the eigenvalue here will be 2 into minus 1 square minus 3 into minus 1 plus 4 into identity is 1. So this is the eigenvalue of matrix 2A square minus 3A plus 4I corresponding to the eigenvalue minus 1 of matrix A. And similarly for 3 you will get 2 into 3A square minus 3 into 3 plus 4 into 1. So these are the two eigenvalue of this matrix 2A square minus 3A plus 4I. So this was some polynomial expression in A. And we knew the eigenvalue of matrix A. So if you want to calculate eigenvalue of this polynomial, simply replace A by lambda. So this is second part of fourth property. So these are the first four properties. Now after this we have to learn the other two properties which are related with eigenvalue of symmetric, skew-symmetric, Hermitian and skew-Hermitian matrices. So our fifth property is, okay, so now the other two properties are related with symmetric, skew-symmetric, Hermitian and skew-Hermitian matrix. So the fifth property is the eigenvalues of a symmetric means A transpose is A. This we have discussed earlier. So eigenvalue of a symmetric or Hermitian, eigenvalue of a symmetric or Hermitian, the definition of Hermitian was conjugate transpose of A is matrix A. So eigenvalue of a symmetric matrix or Hermitian matrix. Now see, the symmetric matrix is applicable for matrices of real numbers, and if you have matrix of complex number, then this word Hermitian will be applicable. So eigenvalue of a symmetric or Hermitian matrix are always purely real. So this is very important property. Eigenvalue of these matrices, either symmetric matrix or Hermitian matrix, these are always purely real. Now I will explain the idea of this thing with the help of a 2 cross 2 matrix. So suppose if I have a 2 cross 2 matrix and say it is a symmetric matrix. So symmetric matrix means you can have anything on diagonal, but the element Aij is same as element Aij. This was another definition of symmetric matrix. Aij is Aji. So we can take a general example that suppose if I have A here, B here, and if I write C here, and if the matrix is symmetric, then we have to write C here. So suppose this is the matrix that you have, and you are interested in finding the eigenvalue of this matrix. So for eigenvalue, you have to solve the characteristic equation determinant of A minus lambda I equals to 0. So this will give you A minus lambda C B minus lambda, this equals to 0. You have to subtract lambda from the diagonal elements. So now if you expand this, then you will get A minus lambda B minus lambda minus C square, this equals to 0. So which will give us lambda square minus A plus B into lambda plus AB minus C square, this equals to 0. So this is the characteristic equation to find eigenvalue. Lambda square, let me write the equation here. So lambda square minus A plus B lambda plus AB minus C square, this equals to 0. So this equation will give us the eigenvalue. Now we have to prove that the roots of this equation are real, because this matrix that we have taken, this was a symmetric matrix. So see, this is a quadratic equation in lambda, lambda square, then lambda, and then this is your constant term. Now we know that in a quadratic equation, ax square plus bx plus c equals to 0. If we want to check whether the roots are real or imaginary, then we have to calculate the discriminant. So, and the discriminant is nothing but b square minus 4ac. This we have learned in class 10. Now there are three possibilities for discriminant. Either discriminant is positive, or it is 0, or negative. If discriminant is positive, this means real and different root, real and distinct roots. If discriminant is 0, then in that case you will get real and equal roots. And if the discriminant is negative, then in that case you will get imaginary roots. So these concepts we already know from class 10. So this is the quadratic equation that we have, and we want to find whether the roots of this quadratic equation are real or imaginary. So in the first two cases you will get real roots, either the discriminant is positive or 0, and if the discriminant is negative, then you will get imaginary root. So the discriminant of this quadratic equation, it is a quadratic equation in lambda. So the discriminant of this quadratic equation will be b square. Now b is nothing but coefficient of lambda. So I will get a plus b square. We have minus sign here, but if we square, then that minus will become plus. So this will be your b square minus 4 into a is 1. A is the coefficient of lambda square here. So a is 1 and c is ab minus c square. So this is your discriminant. Now you can write this thing as a square plus b square minus 4ab plus 4c square. So this will become, a square plus b square plus 2ab, a square plus b square plus 2ab minus 4ab plus 4c square. This is your discriminant of the quadratic equation in lambda. Now I can write this thing as plus 2ab minus 2ab, so this will become minus 2ab. So first 4 term, this will give you a minus b whole square plus 2c square. Now you can see that these are perfect square. A minus b square is perfect square, and this 2c square is also perfect square. And we know that if a and b are real numbers, c is also a real number. So in that case, perfect square is always positive. Always positive or 0. So this means your first term is always greater than equal to 0. Your second term is also always greater than equal to 0. So this means if you add these two terms, then you will get either some positive number or 0 in case if both the terms are 0. So this means d of lambda is always greater than equal to 0, which implies real roots, and roots are nothing but eigenvalues. So this implies real eigenvalues. So I have taken a very basic example of 2 cross 2 symmetric matrix, but you can show that for any symmetric matrix, in case of matrices of real numbers, and Hermitian matrix in case of matrices of complex number, the eigenvalues are always purely real. Now this property is, questions based on this property has been asked in GATE on 2 or 3 occasions. So you should know this property. If you have a symmetric matrix or Hermitian matrix, then eigenvalue will be always purely real. So this was the 5th property. Now the next one is related with skew-symmetric matrix. So now we are going to discuss the 6th property. Property number 6 is eigenvalue. 6th property is eigenvalues of a skew-symmetric, eigenvalues of a skew-symmetric or a skew-symmetric. The definition of a skew-symmetric was A transpose is minus A, or a skew-Hermitian. So the definition of a skew-Hermitian matrix was conjugate transpose of A is minus A. A skew-symmetric simply transpose is minus A. A skew-symmetric A transpose is minus A. A skew-Hermitian conjugate transpose of A is minus A. So in case of these two matrices, either skew-symmetric or skew-Hermitian, the eigenvalues are always purely imaginary. Eigenvalues are always purely imaginary or zero. Purely imaginary means the real part is zero. See, if you have a complex number, any number can be written in the form of complex number. So z is x plus iota y. X is the real part of z. This x is called real part of z, and y is called imaginary part of z. So if x is 0, this means z is purely imaginary. Z is purely imaginary. So example of these type of complex number are, say z is 4 iota. So this is purely imaginary complex number because the real part of this complex number is 0. And if y is 0, this means z is purely real. So if z is some number, say if z is equal to 2, so this complex number is purely real complex number because the imaginary part is 0. So in case of symmetric or Hermitian matrix, the eigenvalue are always purely real, and in case of skew-symmetric and skew-Hermitian matrix, the eigenvalue are always purely imaginary or 0. You can prove this property using the same technique. Suppose if I have to show that eigenvalue of a skew-symmetric or a skew-Hermitian matrix are always purely imaginary. So again I will take a 2 cross 2 matrix just to explain the idea of, just to explain this concept. So suppose if I have a 2 cross 2 matrix, say the matrix that I have is 2 cross 2 skew-symmetric matrix I am taking. So we know that in case of a skew-symmetric matrix, the diagonal elements are always 0. So we have to write 0 on diagonal, and Aij, this was the definition of skew-symmetric, Aij is negative of Aj. So this means here if I write A, then this element will be minus A. So this is a general example of 2 cross 2 skew-symmetric, 0 on diagonal, A then minus A. Now in order to find the eigenvalue of this matrix, you have to solve the characteristic equation. So this will be determinant of A minus lambda equals to 0, which means we have to subtract lambda from the diagonal element. So minus lambda A minus lambda, this will be 0. Now if you expand this, you will get lambda square plus A square, this equals to 0, which means lambda square is minus A square. This you can write as lambda square. Minus 1 you can write iota square. A square, we know that iota is nothing but root over minus 1. So minus 1 will be iota square. So this means the value of lambda will be plus minus iota A. So these are the eigenvalue of this matrix A. So as you can see that this eigenvalue is purely imaginary, the real part is 0. Or if A is 0, in that case the lambda will be 0. So the important thing is that in case of a skew-symmetric or a skew-Hermitian matrix, the real part of eigenvalue is 0. The real part is 0, which means the eigenvalue is either purely imaginary if A is non-zero, and if A is 0, then in that case the eigenvalue is 0. So therefore I have written here that in case of these two type of matrices, eigenvalue are either purely imaginary or 0. Purely imaginary means those type of complex number whose real part is 0. So these are the 6 properties of eigenvalue. Now after this we will see some of the problems which were asked in GATE previous year based on the properties of eigenvalues. Okay, so our first problem on eigenvalue is, this question was asked in GATE 2013. The problem is the minimum eigenvalue of this matrix is. You have to find the minimum eigenvalue. Now see, one approach is that solve the characteristic equation. Now here you will get a cubic equation and find all the 3 eigenvalue and then see what is the minimum eigenvalue. Or you can see from the options that the minimum option that is given is 0. Now if we can show that 0 is one of the eigenvalue of this matrix, then this will be our correct answer. So see, first we have to calculate the determinant of this matrix. We have learned that in case of, we have learned in properties of eigenvalue that sum of all eigenvalue is equal to the sum of diagonal elements, and product of all the eigenvalue is equal to the determinant of the matrix. So for these type of problem, always calculate the determinant of this matrix. Now determinant of this matrix will be, if I can expand along the first column, or maybe we can perform this operation, you can see that if I add first and third row, then I will get the second row. So if I perform this operation, say R2 goes to R2 minus R1 minus R3, then in that case our matrix A, this will become first row will be 3, 5, 2. The second row is second row minus first row minus third row. So I'll get 5 minus 3 minus 2, 0 here. 12 minus 5 minus 7, 0 here. 7 minus 2 minus 5, 0 here. And 2, 7, 5. We are interested in calculating the determinant of this matrix A. So if I want to calculate the determinant of A, then we know that if I perform this operation, then it will not change the value of determinant. Now you can see that this R2 is completely 0, and therefore we can say that the determinant will be 0. So since the determinant of this matrix A is 0, this implies that product of all the three eigenvalue lambda 1, lambda 2, lambda 3, this will be 0, which means at least one of the eigenvalue, whenever the determinant of a matrix is 0, so in that case at least one eigenvalue has to be 0. Now from the options you can see that the minimum option that is given is 0, and we know that 0 is one of the eigenvalue, so therefore the minimum eigenvalue will be 0. Now if any other option was there which is less than 0, then obviously you have to solve the characteristic equation to find all the three eigenvalue, and then you have to see which one is the minimum. But here the minimum option was 0, and we can directly see that 0 is one of the eigenvalue, and therefore the correct answer is 0. So this was very simple question. This was asked in GATE 2013 for 2 marks. Now the next problem is, again this question was asked in GATE 2009. Now the problem is the eigenvalue of the matrix R. This matrix A is given, 4 options are given, and you have to identify which option is correct. So we have learned that the sum of all the eigenvalue, we are going to eliminate from the options. It is always better to eliminate from the options in any GATE problem. So sum of eigenvalue, this we have seen, is equal to sum of diagonal elements, which is called a trace of the matrix. So sum of all the first we are going to calculate the trace of the matrix, and then from the options we will see which option will satisfy this condition. So here the trace of the matrix will be, if I add all the diagonal elements, then I have minus 1 plus 3. So I'll get minus 1 plus 3, which is 1. So sum of all the eigenvalue has to be equal to 1. Now if you see the first option, if I add all these 3, then I will get 3 plus 6, 12. So 12 minus 4 iota, and therefore this option A is incorrect. Sum is not equal to 1. Now option B is minus 6 plus 3 plus 3. So this will give you 0, and you will get some imaginary part. So this is also not correct. We have to get the sum as 1. Now in option C also you can see that 3 plus iota, 3 minus iota, 5 plus iota. Now here also if you add, then you are not going to get the sum 1. So this option C is also incorrect. And finally our option D is 3 minus 1 plus 3 iota minus 1 minus 3 iota. So the correct answer, if you add all these numbers, then you will get 3 minus 1 plus 1 plus 3 iota minus 3 iota. This will cancel. So this is your correct option D. Now see, this was a very simple problem because of the options that were given, and you don't even have to calculate the trace. If you know one important property of any polynomial equation, then you don't even have to see, you have to calculate the trace. Simply by seeing the option you can tell what should be the correct answer. So the property is something like that, that the imaginary roots of a polynomial equation, with real coefficients. This point is very, very important. The imaginary roots of a polynomial equation with real coefficients. If all the coefficients are real numbers, then the imaginary roots of a polynomial equation. So the imaginary roots of a polynomial equation with real coefficient always occur in conjugate pair. So this point is very, very important. Now from the options you can see that only option D is having imaginary roots in conjugate pair. First let me explain what is the meaning of this conjugate pair. So suppose if I have a equation, say suppose if I have a cubic equation, okay, suppose if I have this equation, say a lambda cube plus b lambda square plus c lambda plus d, this equals to 0. And suppose it is known that this equation has one imaginary root. So this cannot have one imaginary root. Either it will have imaginary root is always in pair. This property is imaginary roots of a polynomial equation with real coefficient. So if these coefficients a, b, c, d are real numbers, then imaginary root will always be in pair. So this means this equation will have either all three roots. Only two possibilities there. The first possibility is all three real roots, or it will have, or the second possibility is that it will have one real plus two imaginary roots. One real plus two imaginary roots, and the imaginary roots will be always in pair. So if it has one real and two imaginary roots, so suppose if one root is say alpha and other root is say beta plus iota gamma, then the third root has to be the conjugate of this root, so beta minus iota gamma. So these are the three roots if it has one real and two imaginary root. Now from all the options you can see that only option D is having imaginary roots in pair, 1 plus 3 iota, 1 minus 3 iota. Here you have three imaginary roots, which is not possible because imaginary roots are always in pair if it is a polynomial equation with real coefficient. Now here, since all these entries are real numbers, so therefore you will always get real coefficient. So you cannot have three imaginary root. Here also you cannot have three imaginary roots, and if you are having two imaginary roots, then it has to be in conjugate pair. Here we are not getting conjugate pair. This is 3 plus 5 iota, so the other root has to be 3 minus 5 iota. So this is very, very important point. Here you can directly solve this problem using the concept that we have just learned. Trace is the sum of eigenvalues. But if you know this property, then this will be very helpful for some other problems. So these were the two basic questions on eigenvalue. After this we'll see some other problems based on the eigenvalue. Okay, so our next question is, this question was asked in 2016 in computer science. If the two eigenvalues of a 3 cross 3 real matrix means all the entries are real. So if two eigenvalues of a 3 cross 3 real matrix are 2 plus iota and 3, then find the determinant of the matrix. Now again, this is a very simple problem once you know the properties of eigenvalue and the concept that we have just learned now. So we know that that determinant of any square matrix is nothing but product of eigenvalue. This was our first property. So product of all the eigenvalue, this will give you the determinant of matrix A. But the problem is only two eigenvalues are given. One eigenvalue lambda 1 is say 2 plus iota, and the other eigenvalue lambda 2 is 3. Now the question is, if we can find the third eigenvalue, then you can easily find the determinant of the matrix. And the concept that we have just learned is that imaginary roots of any polynomial equation with real coefficient. Now it is given that this matrix is real, so this means coefficients will be also some real numbers. So imaginary roots of any polynomial equation with real coefficient always occur in conjugate pair. So this means if one root is given, one root is 2 plus iota, the other root has to be 2 minus iota. And once you know all the three eigenvalues, then you can easily calculate the determinant. The determinant of this matrix will be lambda 1 is 2 plus iota, lambda 2 is 3, lambda 3 is 2 minus iota, and the product of these three eigenvalues, this will give you the determinant. So this will be 3 into a plus b, a minus b, so a square minus b square. Iota square is minus 1, so minus iota square, this will be plus 1. So 3 into 2 square plus 1, 5 into 3, 15. So this means the determinant of this matrix A, whose eigenvalues are given, will be 15. So this is your correct answer. So this was very simple problem. You had to know how to find the third eigenvalue, and you had to know this property that determinant is nothing but product of eigenvalue. So this was our third problem based on eigenvalue. Now the next question is, this was asked in GATE 2016. The problem is a square matrix A has these three eigenvalues, 1, minus 1 and plus 3. The question is, you have to find the trace of a cube minus 3a square. Trace means sum of the diagonal elements. So we have learned that sum of eigenvalues lambda 1 plus lambda 2 plus lambda 3 up to lambda n, this is nothing but the trace of matrix. So if we are interested in finding trace of this matrix A cube minus 3A square, then first we have to calculate the eigenvalues of this matrix, and then trace will be nothing but sum of those eigenvalues. Now see, eigenvalue of matrix A is given. The eigenvalue of matrix A is minus 1, plus 1 and 3. And we have to find the eigenvalue of this matrix A cube minus 3A square. Once you know the eigenvalue, then you can easily find the trace of this matrix, because trace will be nothing but the sum of eigenvalue of this matrix. Now see, there are three possible eigenvalue. So I'm going to draw three arrows, and corresponding to minus 1, if I want eigenvalue of matrix A is minus 1, so eigenvalue of A cube minus 3A square, this will be minus 1 cube minus 3 into minus 1 square. Okay, simply substitute this number minus 1 here. We'll see how this property is derived when we discuss eigenvectors. But we have seen this was our third or fourth property. This was our fourth property. So corresponding to minus 1, the eigenvalue of this matrix A cube minus 3A square, this will be minus 1 cube minus 3 into minus 1 square. Simply replace this matrix A by the eigenvalue minus 1. So this will be minus 1 minus 3. This will become plus 1. So finally you will get minus 4. So this is the eigenvalue corresponding to minus 1. Then corresponding to eigenvalue plus 1, here you will get 1 cube minus 3 into 1 square. So this will be 1 minus 3 minus 2. And finally corresponding to this number 3, you will get 3 cube minus 3 into 3 square. So this will be 27 minus 27, 0. So these are the three eigenvalue, minus 4, minus 2 and 0 of the matrix A cube minus 3A square. Now once you know the eigenvalue of this matrix, you can easily find the trace of this matrix. Trace of A cube minus 3A square, this will be the sum of all eigenvalues. There are three eigenvalues. So first eigenvalue minus 2, minus 4, minus 2 plus 0. So this will be minus 6. So the correct answer for this problem is minus 6. After this, we'll take one more problem on eigenvalue, and then we'll talk about eigenvectors. Okay, so our next question is, this is very interesting problem. This was asked in GATE 2017. The question is, consider a 5 cross 5 matrix. Now this matrix A is given. It has 5 rows, 5 columns. The first row is 1, 2, 3, 4, 5. Similarly, it has the other rows. Now one of the real eigenvalue of this matrix A is, 4 options are given, and we have to find that which one is correct. Now see, this is a very interesting problem. We'll discuss this problem in detail, and from this problem we will also derive one very important formula. So in order to find eigenvalue, basically we have to solve characteristic equation. Now this characteristic equation is nothing but determinant of A minus lambda I equals to 0. So here our characteristic equation will be, this is our matrix A, and we have to subtract lambda from all the diagonal elements. So I will get 1 minus lambda, then 2, 3, 4, 5. This will be our first row. Then our second row will be 5, 1 minus lambda, 2, 3, 4. The third row will be 4, 5, 1 minus lambda, 2, 3. Then 3, 4, 5, 1 minus lambda, 2. 2, 3, 4, 5, 1 minus lambda. Now we are not going to expand this determinant, so don't worry. We are simply going to, if you see this, we are going to add all these elements. If you add all these elements, then you will get 1 plus 2 plus 3 plus 4 plus 5. So this will give you 15 minus lambda. Similarly, if I add this all the elements of this second row, then you will get 5 plus 1 plus 2 plus 3 plus 4, 15 minus lambda. So you can see that sum of all the elements, in all the 5 rows, columns, is some constant. The constant is 15 minus lambda. So here if I perform this operation, C1 goes to, we know that in case of determinant, this will not change the value of determinant. So if I perform this operation, C1 goes to C1 plus C2 plus C3 plus C4 plus C5. Then I will get 15 minus lambda in first row of column. Each element of the first column, this will become 15 minus lambda. And then you will have second column, third column, fourth column, fifth column. This equals to 0. I am not writing these elements because that is not important. We are only going to consider this first column. Now if I take 15 minus lambda outside, we can take any element common from any row or column. So if I take 15 minus lambda outside, then I will get a 5 cross 5 determinant, and this is equal to 0. Okay, we can take, since we have 15 minus lambda in each element of the first column, we can take this outside. Now here you have a 5 cross 5 determinant, this determinant, the first column will become 1 1 1. So now you have these two terms, one is this 15 minus lambda and the other is this 5 cross 5 determinant, and the product of these two is 0. So this means at least one of them has to be 0. So 15 minus lambda, this will be 0, which will give you lambda equals to 15. So this means one of the eigenvalue of this matrix is 15. Now from here you can derive one very important conclusion. See, this 15 is nothing but sum of all the elements. If I add all the elements in a row or column, then I will get 1 plus 2 plus 3 plus 4 plus 5, 15. Similarly, you can see that all the elements of second row, third, fourth and fifth row is also 15. So from here you can derive one very important conclusion, that if the sum of all elements in a row or column of a matrix, if the sum of all the elements in a row or column of a matrix is constant means some fixed number, then that constant has to be one of the eigenvalue, of the matrix. So this is very important point. Once you know this result, then you don't have to do any calculation. You can simply see the matrix and you can see that sum of all the elements is constant. So the constant is 15. So this means 15 has to be one of the eigenvalue. Now let me take one example to explain this concept further. Suppose if I have a matrix A, this problem is over, the correct answer is 15. Now suppose if I have a matrix A whose first row is say A, B, C, second row is B, C, A, and the third row is C, A, B. Suppose this is a 3 cross 3 matrix that you have. And so if you see this matrix, if you add all the elements of all the 3 columns, then you will get A plus B plus C, B plus C plus A, C plus A plus B. So sum of all the elements of all the 3 columns is constant, and therefore you can say that one of the eigenvalue of this matrix has to be that constant A plus B plus C. So you don't have to do any calculation. You can directly say that this A plus B plus C, this will be one of the eigenvalue of this matrix. So this was our last problem on eigenvalue. After this, we'll talk about eigenvectors.